Okay, welcome back. So, what is a mass spectrometer? You might remember that in Unit 1 chemistry we talked about isotopes. The mass to charge ratio of isotopes is measured using a mass spectrometer. The output from this can be used to calculate relative atomic mass. This year, we're going to use mass spectrometry to help solve problems involving the identification of organic compounds. You don't need to know how the mass spectrometer works to answer exam questions, but a little bit of understanding will help you to understand why fragments that appear in the final spectrum are positively charged. So what happens is the sample is injected into the mass spectrometer and a high energy electron beam is fired at the sample. You've got some magnets which accelerate the ions that are formed. Anything that is neutral or negatively charged is evacuated, so it doesn't make it through to the spectrum. So here we have our positive ions that are deflected around a corner depending on their mass to charge ratio, and they end up on the mass spectrum. So this lesson we're going to look at the principles of mass spectrometry that's used to identify organic compounds. We're going to look at the applications of mass spectrometry and interpretation of qualitative and quantitative data, including the identification of the molecular ion peak, the determinant of molecular mass, and how to identify simple fragments. Okay, so we'll look at the principles of mass spectrometry first. Only positive ions make it through to the mass spectrum. So all of these lines that we can see on this spectrum are all positively charged. This is an example of a mass spectrum of ethanol. Ethanol is an aldehyde with 2 carbons. So on the y-axis, we've got the relative or percentage abundance, and on the x-axis, we have mass to charge ratio, and the symbol is normally m/z, but sometimes you will see m/electron. The base peak is the most abundant ion fragment, and it's where all the other percentages of abundance are measured against. So if it's 100%, then everything else is less than 100%. The molecular ion peak is normally to the very right of the spectrum, and it's equivalent to having the molecular formula with 1 less electron, with 1 electron missing. Okay, mass spectrometry is actually a destructive technique. Some of the other techniques we're going to look at don't destroy samples, but this one does. We can see that the sample gets injected, it gets bombarded by a high energy electron beam. The positive fragments, the positive ions, are accelerated through this electromagnet and deflected. And the extent of the deflection depends on 2 things. It depends on the mass of the ion. So the lighter the ion, the greater the deflection, and also the charge on the ion. The greater the charge, the greater the deflection. And what we need to be able to do is interpret the output on the mass spectrum. Okay, so coming back to our mass spectrum of ethanol, we already looked at the base peak before. The molecular ion peak, which is given the symbol M, capital M plus, is a positively charged ion of the molecule. It corresponds to the molecular ion which has the highest mass to charge ratio. So if we think about the molar mass of CH3CHO, the molar mass would be 2 lots of carbon plus 4 lots of hydrogen plus 1 lot of oxygen equals 44 grams per mole. That 44 grams per mole, if this is 41, 42, 43, and this is 44, the 44 grams per mole is equivalent to 44 mass to charge ratio. Now, because electrons have negligible charge compared to protons and neutrons, the molar mass of positive fragment is going to be virtually the same as the molar mass of the molecule. So to form the molecular ion, this is the equation that you need to remember. So we have the molecule, which has got the symbol M, And I'm afraid we use capital M a lot in chemistry, but in this case it's talking about the molecule. We bombard it with a high energy electron. What we end up doing is producing the molecular ion, positive ion, and 2 electrons, one that came from the original molecule and one that was the source of the firing of the electrons. So if we think about ethanol, we said before that it's an aldehyde. This is its structural formula. It has a molar mass of 44 grams per mole. This equates to the molecular parent ion at 44 mass to charge ratio. If we go back to look at the spectrum, we can see that there's another signal at 45 mass to charge ratio. That line is due to a fragment that contains a 13 carbon isotope. So either this carbon is 13 or this carbon is 13. So we have, instead of CH3CHO with 12 carbon and 12 carbon here, one of the carbons is the 13 carbon isotope, which means that it's got an extra neutron, so it actually has a line at 45 mass to charge ratio. And if we go back and have a look at it again, we can see that the relative abundance is much smaller than the main parent molecular ion. And that's because 13 carbon is a pretty rare isotope of carbon. Okay, let's look at a worked example. We're told we have an unknown molecule. It's called J, and it contains chlorine. We're told that the relative molecular mass, in other words, without units, is 108.5, and there's no units because it's relative. The first thing we're asked to do is explain the presence of the peak at 110 mass to charge ratio. Well, this is another parent molecular ion, but it's due to an isotopic effect. So the most common isotope of chlorine is 35 chlorine. But instead of 35 chlorine, if we have 37 chlorine, then we're going to have another 2 mass charge ratio. So this could be using 35 chlorine, and this one could be with 37 chlorine. There's 1 mark for referring to that. Part B, explain how the peaks in the mass spectrum relate to the molecular mass of the molecule. So we have 2 peaks, one at 108 and 110. They're both parent molecular ions, so they're both M+. The relative molecular mass is a weighted average of the 2 parent ions based on their relative abundances. One contains 35 chlorine and the other contains 37 chlorine, and that's why we have 2 of them. But you can see that at 110 mass to charge ratio, the percentage abundance is lower because the 37 isotope of chlorine is also lower. Okay, now we're going to try and explain some of the other peaks that we see on a mass spectrum. Base peak, we've been told before, is the peak all the other percentages, abundances are measured against. So it is generally either the most abundant or most stable, or can be formed in multiple ways of forming. But that doesn't explain why we have all these other little peaks on the mass spectrum. What happens is that to make the molecular ion, the molecule loses a single electron. So the molecular ion for the ethanol CH3CHO+, that's then unstable, and it can further fragment into other ions. If it loses a hydrogen off the methyl group, then it's CH2CHO, and if it's still retained a positive charge, then that's got a plus. And the hydrogen with an unpaired electron is also expelled. Now, an unpaired electron is not an anion. It's a free radical, which is a species with an unpaired electron in an atomic orbital, and it's highly reactive. Now, neutral or negative ions won't make it through to the mass spectrum, so that would be evacuated and not appear on the mass spectrum. The other thing that could happen when we fragment ethanol is that hydrogen ions could make it through, and we might have down here at around 1 mass charge, or less than 10. We might have a 1 that is showing this positive fragment, and then this radical could be removed. Or we could start off with the molecular ion and maybe it fragments. So the CHO plus is the part that gets through and a methyl radical is lost. Or the methyl radical makes it through and that would be to 15 mass charge ratio. And this other fragment is lost or evacuated. Many covalent bonds in the molecule, the parent molecular ion, that could be broken to form other fragments. If we look at a different example, here we've got propanoic acid. Now, propanoic acid, remember, it's got 3 carbons. Propanoic acid, it's got 2 molecular ions, M+, one with 12 carbon, which is more abundant, and another one with 13 carbon. So we could take our propanoic acid molecular ion and then imagine we were to split the molecule here. If that part is positively charged, then that will be this fragment CH3, CH2 plus that gets through. This remaining part here would be evacuated, so not make it through the spectrum. That's the free radical. Or alternatively, if we put the plus charge on the carboxyl group, then that fragment would make it through and this part here would be evacuated. So we can start seeing how we could get various fragments. So remember, all the fragments are positively charged because only positive ions make it through to the mass spectrum. If we have CH3+, that's got a mass charge ratio of 15. So 1 times 12 and 3 lots of hydrogen. OH plus, now we often think of hydroxide as an anion, but remember only positive fragments make it through. That would be 1 lot of 16 and 1 lot of 1. So that could be an OH hydroxyl group that's been protonated. Here we've got 2 different groups of atoms that can make a mass charge ratio of 29, which means that that's making it relatively more abundant because it can be made multiple ways. If we have the isotope 35, we might get some 35 chlorine coming through that's positively charged, or 37 chlorine if that was present. Obviously not going to be in propanoic acid. But the propanoic acid could have COOH plus, and that would have a peak at 45. So that starts to explain some of the peaks that we see on the mass spectrum. Okay, let's look at another worked example. The mass spectrum of an unknown compound that contains carbon, hydrogen, and oxygen is shown. Write the chemical formula of the species that produces a peak at mass charge ratio 43. So to produce a peak, it must be positively charged. So there's a number of options that we could have that end up with a mass charge ratio of 43. It could be CH3CO plus, or it could be CH3 twice CH, or it could be C2H3O, or it could be C3H7. There's a whole lot of possibilities at mass charge 43. So as long as we identify one that has a positive charge, any of those combinations would be fine. Okay, let's summarise what we've learnt. Only positive ions are recorded on the mass spectrum. So anything that's negative or neutral will be evacuated from the machine and won't end up on the spectrum. The molecular or parent ion, which is given the symbol capital M+, is used to identify the molar mass or the relative molecular mass of a compound. And it tends to be the last peak or set of peaks towards the right of the spectrum. Multiple parent ion peaks indicate the presence of one or more isotopes, of multiple isotopes, I should say. To form the molecular ion, we get the molecule, we bombard it with high energy electrons to remove an electron, so we've got the parent molecular ion, and we end up with 2 electrons, one that came from the original molecule and one that did the damage and the destructive technique. The base peak is the most abundant peak, so in this example, this is the base peak and the molecular ion peak, and it corresponds to the most stable fragment or to the mass-charge ratio that can be made in multiple ways. Once a molecular parent ion has been formed, it can further fragment. For example, propanoic acid, here's our molecular ion. We can break a bond to have an ethyl group or to have a carboxyl group that will make it through, and the neutral free radicals will be evacuated and not appear on the mass spectrum. Okay, I'll see you next time. Bye.